In this video, we're going to look in a little bit more detail at the Big Bang and theories surrounding the development of the universe. In 1931, Georges Lemaitre suggests that the universe started out as a single space particle. In 1948, George Gamow suggests that the universe started as a hot, dense concentration of matter that exploded out to its present form. In 1950, Fred Hoyle calls it a Big Bang. And in 1970, Stephen Hawking and Roger Penrose proved mathematically that the universe began with a Big Bang. The Big Bang theory is now widely accepted as there is much evidence to support it. We've already looked in previous videos at cosmic background radiation. We also know that there are relative proportions of lighter elements. There's the Hubble expansion, obviously using redshift to show that galaxies are moving away from us. It's imperfect and it continues to be modified as new evidence becomes available. But the current model suggests that an initial rapid inflation led to a more slowly expanding, spatially flat universe, and now it is accelerating in this expansion. So when did it happen? Well, using quantum mechanics, the universe started as a Big Bang about 13.7 billion years ago. The Big Bang was the beginning of space and time. There was no before, there was no outside. All that was present was energy. The first minutes of the universe released energy which changed to matter, forming stars and galaxies. At 10 to the minus 43 seconds after the Big Bang, time and space began to behave in a way that we now understand. This is called Planck time. If you want to have a look for some more details, have a look at your notes. Page 7 for a timeline. There's lots of ways that we can look at the timeline of development, and if you just go out onto Google and search images, you'll find many illustrations such as this one that show you a timeline for the development of stars. And again, if we look at the no beginning point down here, we can see that 10 to the minus 43 seconds here is the beginning of Planck time. And now we have space and time above this till we get to the present day. Here again we can see 0 to 10 to the minus 43 seconds as the Planck era. We've got the Big Bang followed by a rapid inflation, quark soup. Then we get to eventually the modern universe down here. So of course radiation dominated the early universe from the radiation from photons, and now the universe is dominated by matter. Some radiation from stars and microwave background radiation. Now we need to know about the fundamental forces in the universe. We have the strong nuclear force which acts on protons and neutrons over extremely short distances. We have the weak nuclear force which acts on electrons, quarks and muons, they're elementary particles. Electromagnetic forces, which we've talked about in our previous unit, which acts on electrically charged particles. And then gravitational force, which is the force that exists between any objects that consist of matter. So let's have a look. 10 to the minus 43 seconds after the Big Bang, very short space of time. Space and time do not exist. The temperature is in trillions of degrees, and of course there is no matter. There are 4 basic forces combined into a single superforce, and quarks start to combine to form photons, positrons and neutrinos, along with equivalent antiparticles. By 10 to the minus 36 seconds, gravitational force separates from the other forces. Energy is so high that there is continual creation and annihilation of particle-antiparticle pairs. 10 to the minus 10 seconds, the temperature falls from 10 to the 29 Kelvin to 10 to 15 Kelvin, and the strong nuclear force splits off. At 10 to the minus 3 seconds, all forces have now separated. Temperature is still too high to form neutrons and protons. But the universe is now filled with radiation in the form of photons, quarks, leptons, and all the antiparticles to the above. At 1 second, the temperature falls to 10 billion degrees. Now this has big implications. The universe now has a sea of protons, neutrons, electrons, positrons, photons and neutrinos. At 3 minutes after the Big Bang, the temperature falls to 1 billion degrees. Protons and neutrons slow down, allowing for nucleosynthesis to occur, basically the formation of the nucleus of what will become atoms. Now we are 300,000 years after the Big Bang. The temperature has fallen to a much more agreeable 3000 degrees Kelvin. Electrons can combine with nuclei to form the first atoms. Light can now be seen. Photons are no longer trapped inside matter. This event defines the observable limits of the universe. Atoms form, followed by galaxies, stars and planets. And here we can see some fundamental particles. We have the electron neutrino, Nancy, muon neutrino, Mookie, tau neutrino, Tim. Now we have our negative electric charge, the electron, Ellie, muon, Mustafa, and tau, Tammy. And here we can see an illustration of leptons and quarks. Now, 15 billion years after the Big Bang, the universe exists as it is now. So here we can see another representation of the formation of the universe. We start with the Big Bang at the bottom. This is followed at 10 to the minus 2 seconds with a sea of trapped light. At about 300 seconds, recombination is occurring. We've got deuterium, helium, lithium forming. At about 380,000 years after the Big Bang, we have neutral atoms. The universe is now transparent and black. And about 1 million to 1 billion years after the Big Bang, we have the formation of proto-galaxies, the precursors of galaxies. So what's the evidence for the Big Bang theory? We've already examined that the universe is expanding from redshift, first described by Hubble. We have the origin of background radiation, nucleosynthesis of the light elements, formation of galaxies, the presence of a large amount of helium in all stars, and the large number of bluer stars in deep space compared to nearby. Okay, so let's have a look at the evidence of redshift. We know that Hubble first stated that galaxies emit light, and if it's redshifted, then the galaxy is moving away from you. So what it means is that the lines in the spectrum are closer to the red end of the light than expected. And because of this, the galaxy must be moving away from us. Space is expanding itself and it's carrying the galaxies with it. It's not that the galaxies are moving through space that already exists. And we can see in this diagram, we have got spectral lines of a galaxy moving towards us. And we can see that the individual spectral lines are shifted towards the blue end of the spectrum down here. So these are these black lines here, which represent the different wavelengths of light being emitted. If a galaxy is at rest, it's neither moving towards you or away from you, we will get a set of spectral lines that look like this one here, the second one. And if it's moving away from you, we're going to get our lines shifted towards this end, the red end of the spectrum. And we can quite clearly see the difference between this top one and the bottom one, denoting the direction that galaxies are travelling. So more evidence. We've already briefly looked at cosmic background radiation. The radiation from the early universe must be somewhere in the universe. Microwaves were detected in the early 1960s, and we'll recall that this was by accident, and the discovery of this afterglow is proof of the Big Bang. Further evidence exists, nucleosynthesis. So the creation of elements occurs in nuclear reactions. The Big Bang predicts that the universe would be composed of 90% hydrogen and 10% helium. These are the smallest elements. And this is consistent with the current composition of the universe. course, formation of galaxies is further evidence. This uniformity was predicted by Friedmann, and the degree of lumpiness explains the formation of stars and galaxies. And we'll examine that in a little bit more detail when we look at accretion. So, formation of galaxies. What we have is a huge cloud of perfectly evenly distributed matter that can never condense into stars because pull of gravity is equal in every direction. So, could this lead to formation of galaxies? No, it couldn't. The clouds grow in density, they accrete and gather, and more matter is attracted to a cloud. Clouds formed in this way are called protogalaxies, and protogalaxies become galaxies through the process of accretion. And there are some incredible images now coming to us from the Hubble Space Telescope showing these birthplace of galaxies. Okay, further evidence is the large amount of helium. The way that stars work, their energy is given off by the conversion of hydrogen to helium through nuclear fusion. All stars contain a lot of helium. This helium is more than could have been produced by their fusion processes. So the production of helium as soon as protons and neutrons are formed is predicted by the Big Bang. Further evidence is the large number of blue stars. We'll start to look at the colours and intensity of light related to temperature when we look at the Hertzsprung-Russell diagram, but the more distant galaxies are more primitive and simpler than complex galaxies around us. Blue stars are very hot. They are born, glow and die in a much shorter time than our Sun, suggesting galaxies formed in the past were different to galaxies of today. Early galaxies and stars formed from gravitational collapse of matter, where matter was more densely distributed. Our Sun is a second-generation star, formed 5 billion years ago from the explosion of a supernova.